Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and graph the two equations in this linear system for today's Bellwork. I'm going to be calling on you to help me out. And so, in this first equation, which form is that linear equation written in? Slope-intercept form, standard form, or point-slope form? So for that first equation, 3x plus 4y equals 11, which form was that? Which form was that? Blake?
That's in standard.
That's in standard form. Good. And so in standard form, we can make a quick graph by finding x and y intercepts. And so for this first one in standard form, I'll go ahead and find my x-intercept and y-intercept, and then make a quick sketch using those intercepts. Recall to find the x-intercept is easy if we're in standard form. We'll simply plug in 0 for y and solve for x. And so if I plugged in 0 for y, that y term would drop out, and I'd be left solving the baby equation 3x equals 11. It looks like x must equal 11/3. And so the x-intercept for that first green equation is going to be x equals 11/3, corresponds with the y coordinate of 0, and I can plot that right on my x-axis now. So 11/3 is 1, 2, 3, and 2/3. So 3 and 2/3 is right about here. We'll try that out. Awesome. The y-intercept I can find alternatively by plugging in 0 for x and solving for y. So if I were to do that, the x term drops off, and I get y equals 11/4, right? 11/4. So that would be the point 0, comma 11/4, and we'll plot that bad boy. That would be 1, 2, and 3/4. So I'm going to go 1, 2, and 3/4, so about here. All right, so let's go ahead and connect that and make a nice line. And it looks like I'd want green to match green. I think it's going to work out. Good. All right, so let's go ahead and consider the next one. The next line is in which form? Slope-intercept form, standard form, or point-slope form? So what's the second equation in? Slope-intercept form, standard form, or point-slope form? Jacques?
It is in slope-intercept. No, yeah.
It is slope-intercept form. It doesn't look like y equals mx plus b. It looks like y equals a plus bx, where a is my start value and b is my rate of change. But it's still slope-intercept form. Good. Go ahead and tell the class the y-intercept when I call your name so I can plot it. So what's the y-intercept in that slightly rearranged second equation? Jarrett? 4. Thank you. So we can go ahead and plot 4 on the y-axis. Then we'll go out and count my slope number, rise over run to get additional points. What's the slope of that second line? Ian? -2. So from this point, we'll go down 2 over 1, down 2 over 1, down 2 over 1. We can even go backwards so long as we count up and back. And now we'll go ahead and sketch a graph. It looks like, oh, it's going to work, it's going to work, it's going to work. I got a good feeling. And yeah, I'm going to do blue. Let's do blue. All right. So now, oh, that didn't do it. How's that? With the win? We want to win. All right. Go ahead and tell the class the solution to the linear system then when I call on you. So what's the solution to this linear system upon graphical inspection? Taylor? 1, 2. Raise your hand if you had 1, 2 as my potential solution point. 1, 2. Keep your hand up if you know how to check. So what can we do to be sure? Great, thanks. Hands down. Rachel?
We can check the table and the calculator.
We can check the table and the calculator. Good. What else can we do to check? All right, what else can we do to check? Megan?
Plug the x and y values into the equation.
Plug the x and y values into the equation. So we've got check with the table and the grapher. We've got plug the x and y into the equation. What's the third way we could use to check? Andrew?
Second calc intersect.
Second calculate intersect. 3 different ways you guys can check your quiz answers before you turn your quiz on day 5. you'll be able to check all the solutions to a linear system by either algebraically plugging in for x comma y and seeing if it makes a true statement, or if it's the calculate aloud portion, you'll be able to scroll down your table, or you'll be able to do second calculate intersect if it's got calculated aloud. All right, so let's go ahead and check scalar potential solution 1, 2. In the first one, 3 times 1 is 3, plus 4 times 2 is 8. Does 3 plus 8 equal question mark 11? Yeah, so the first one checks out. And does 2 equal 4 minus 2 times 1? 4 minus 2 times 1 will be 4 minus 2. Yes, 2 equals 2. So we've got both of those checked out, and I can box it. All right, now let's go to the graph. Except that poor little right paren is just feeling a little bit sad. So we'll go ahead and bolster his day a little bit. We want him to be overshadowed by that left set of parentheses, you know what I'm saying? All right, let's go ahead and check it out. So on my graph, I'm going to go ahead and enter my original y equals 4 minus 2x is the second one. What's that first one? Shoot. How am I going to enter that first one into my graphing calculator? How will I enter that first one in my graphing calculator? Samantha?
You solve so you get y alone on one side.
Absolutely. We have to solve, and so we get y alone on one side, so I can enter into my y equals method. So after solving that, I would subtract over my x term, minus 3x from both sides, and then divide each term by 4, so I get y equals negative 3/4 x plus 11/4. That's what I'm going to enter in my grapher. So y equals negative, can't use that negative, negative 3/4 x plus 11/4. I want to make sure you're comfortable doing second calculate intersect, but first we're going to do Rachel's way. 4 minus 2x. All right, so Rachel's way was, let's go ahead and take a look at my table and scroll. I'm looking for the solution to the system in a table, second graph. I could scroll up or down until I find for a given x value is the same y value produced. And by golly, it looks like when x equals 1, the y coordinate produced in each equation is 2. So we've got a winner here. Looks like right here. The x coordinate of 1 produces the y coordinate of 2 in each case, so the solution point must be 1, 2. And then graphically, again, we can look at our picture. Zoom 6 will return you to a standard viewing window, negative 10 to 10, and then we'll go ahead and do second calculate intersect in order to find that point of intersection numerically. So here we go. Second trace is the calculate menu, and I want the fifth option for intersect. First curve, enter. Second curve, enter. Guess, enter. And voila! The cursor will jump on the intersection point that's nearest to that guess. So it looks to me like the calculator returns the same xy coordinates that we guessed, 1, 2. That's pretty awesome. What questions do you guys have about today's Bellwork? So last time we solved systems graphically, right? Graphically and using tables. Today we're going to solve systems algebraically using pencil and paper methods. We're going to use the substitution method, which you saw in geometry, and then elimination, also known as the addition method or linear combinations, depending upon which textbook you're using or who you're talking to. And so it's called three different names, and we're going to figure out how to use elimination. That's one of my favorite methods. I think you'll like it as well. But first, let's go ahead and take care of our homework check. So at this time, we're going to pause the recording, and if you kindly take out your assignment number 1. Today we're going to solve systems algebraically using strictly pencil and paper methods. And our two methods today we're going to look at are the substitution method and the elimination method. The elimination method is also known as the addition method or linear combinations, and we'll see a reason for that in just a minute. First, though, tables and graphs may not always give exact solutions to a system. We saw last class that there was an intersection point that didn't fall on an integer ordered pair, right? Then we had to guess what fraction was, and there's an infinite number of fractions, right, in between those xy integer coordinate pairs on the lattice grid, and so we are not going to use graphing as a means for solving anytime we have fractional answers. we'll look at methods of finding exact solutions with algebraic manipulation. So one of these pencil and paper methods is called substitution. The substitution method works like this. We want one of the equations to be solved for one of the variables, and sometimes we'll have to rearrange it to make it so. Sometimes we're already given one of the equations solved. So take a look at this. In that first equation in my system, y is already by itself. We know that y and 2x plus 3 are exactly the same. So we can go to the other equation and replace y in that second equation with what y equals. That's 2x plus 3. So now we only need to solve the equations 3x plus 4 times quantity 2x plus 3. That was my y equals negative 42 for the remaining variable x, and then plug it back into the top one for y. So hang tight. We're going to go ahead and do it. I just wanted to show you that's our scheme, right? That's our scheme. Now let's go ahead and do it. So I try to make one of the equations solve for one of the variables. It looks like in this first equation that I'm putting an asterisk by, y is already solved for in terms of x. I'll go ahead and go to the second equation and rewrite it. I'll rewrite that second equation, 3x minus 4y is equal to negative 4 d2, except everywhere I see y, I'm not going to put y, I'm going to put 2x plus 3, what y equals. Let's go ahead and do that now. So 3x minus 4 times y equals negative 42. It's just that y was equivalent to, watch where that lands, 2x plus 3, so that's what I'm going to put in y's place. Everybody see that? So we've just substituted in 2x plus 3 in for y. Now I have a single variable, x, in a single equation, and I've got the tools to solve that. Let's go ahead and do that. I'll distribute to get rid of the parentheses. So minus 8x minus 12. I'll combine my terms. Same side, same operation. I'll add or subtract, multiply or divide to solve for x. So it looks like adding 12 to both sides gets negative 5x equals, and it looks like negative 30. And then we can finish by division. So I'm getting negative 30 divided by negative 5 is positive 6. Is that right? Positive 6? Awesome. After I have my x value, then all I need to do is go into that original asterisk equation, what y equals, and plug in my 6 for x to see what y equals. So I'll go ahead and rewrite y equals 2 times x plus 3, but now I'm going to put in what we found x to be was 6, so I get 2 times 6 is 12 plus 3. So I'm getting 15. However, I'm not going to box 15, right? I'm not going to box 6. Remember, our solution to a system is an ordered pair, x comma y. So go ahead and tell the class what solution I'm going to write down for this linear system, right? What solution would I write down? Joe?
I'm going to be 6, comma 15.
6, comma 15. Awesome. Let's go ahead and check if this potential solution is in fact, right, a solution to the system. We'll see if it satisfies my original. So here we go. I'm going to plug in 15 for y into the first equation. Does 15 equals 2 times 6? It's 12 plus 3. Yes, it does. So the first one's satisfied. Does 3 times 6, 18, minus 4 times 15, that's 60. Does 18 minus 60 equal question mark negative 42? And yes, it does. And so we found a solution to my system 6 times 15. It satisfies each of them in the original. So that's the general scheme for substitution. I want to make sure that one equation is solved for one of the variables. I'll go ahead and substitute what that expression is into the other equation. Everybody see that variable? Solve for the remaining variable, and then plug back into the original asterisk equation. Let's do another. Which equation is solved for which variable in the second example? Right? Which equation is solved for which variable in the second example? Andrew?
X is in the second equation, so we can substitute negative 2y plus 2 in for x in the first one.
Absolutely. We don't have to have y alone, we could have x alone. And so in the second equation, that I'll put an asterisk by, x is already solved for in terms of y. X equals negative 2y plus 2. So Andrew says, let's rewrite the first equation. 3x plus y equals 16, except everywhere we see a y, I'm sorry, an x, we're not going to put x. We're going to put the negative 2y plus 2. That's what x equals. So here we go. 3x plus y equals 16. It's just that x equals negative 2y plus 2. I'm substituting in that expression negative 2y plus 2 in for x because that's what x equals. Bless you. And now we can go ahead and solve this single equation for the single variable y. Watch your signs in parentheses, you guys. So we'll go ahead and distribute negative 6y plus 6 plus y equals 16. Combine like terms, negative 6y plus 1y, same side, same operation. I get negative 5y plus 6 equals 16. Add or subtract, multiply or divide to get my y term alone on one side. Looks like subtract 6 from both sides, I get 10. And I finish it out with division. Dividing both sides by negative 5 gets me my y coordinate. 10 divided by negative 5 is negative 2. So I found my y coordinate. Is there anywhere at all, where we could go and find the corresponding x coordinate? Yeah, that's why I put my asterisk there. That's going to remind me once I get y, I can go ahead and figure out what x is by plugging into that asterisk equation. It looks like x equals negative 2y plus 2. Y we said was negative 2. So negative 2 times negative 2 is positive 4 plus 2. It looks like 6. So I'm going to go ahead and check the potential solution. The potential solution, x comma y. In this case, what will my solution be? Aaron?
6 comma 2.
6
Negative
comma
Negative 2.
negative 2. Thank you. Let's check. So into the original. Here we go. Does 3 times 8, 6, 18 plus a negative 2 equal question mark 16? Yes. Does 6 equal negative 2 times negative 2 is 4 plus 2? Yes, 4 plus 2 does equal 6, so I'm confident in my answer. Awesome. What questions do you have about the second one? Okay, then go ahead and show me you get it. Go ahead and decide which of these equations solve for which of the variables. You can check with your partner so long as you work quietly, and then we'll come back together. Show me that you get it. Let's use substitution to solve this one. Awesome work, you guys. I'm doing great stuff. I'm going to go ahead and rewrite that first equation. 3x plus 4y equals 11. Except everywhere I see a y, I'm not going to put y. What am I going to put? Mark?
4 minus 4.
Absolutely. We're going to replace y with what y equals. 4 minus 2x. In this way, I get a single equation with a single variable, just x's, and now I can solve. So watch your distribution. Plus 16 minus 8x equals 11. Combine my terms, same side, same operation. Negative 5x plus 16 equals 11. Opposite side, opposite operation. Subtract that 16 over and get negative 5x equals negative 5. Dividing both sides by negative 5 gets x alone, and I get x equals 1. Raise your hand if you had the x coordinate was 1. We're not done, but the x coordinate was 1. Where do I go to get the y coordinate? Nathan Z?
Put the x equals 1 equation.
Absolutely. We'll order that second equation and rewrite y equals 4 minus 2x, but we'll put in 1, so we're almost done. We get y equals 4 minus 2 times x. X was 1. So 4 minus 2 times 1 is 4 minus 2, which is 2. So my final answer then, as a point, x comma y, Megan?
1, 2.
1 comma 2. And is this familiar? Is this point familiar? You're like, I don't know, we saw 1 comma 2 earlier. Yeah, algebraically we just verified our Bellwork, right? A fourth way now. We checked with the table, we did second calculate intersect, we checked the potential solution point in the original system, and now we solved using substitution, and we've gotten 1 comma 2 every time. So absolutely right. Raise your hand if you already have 1 comma 2. Who had 1 comma 2? Awesome work, you guys. You got substitution method, that's great. So why was it easy to use substitution method to solve the system, right? What made it easy to use substitution method versus what if the system had been 3x plus 4y equals 16 and 5x plus 2y equals 2? Would it have been just as easy to solve this system? Why or why not? Go ahead and tell your partner the difference between these two, and if substitution method is just as easy to use in that second case. Why or why not? All right. So would substitution method be just as easy to use for that second one? Right? Would substitution method be easy to use for that second one? Jacob and Emily? Jacob says no because it doesn't have x by itself, right? The way that the first one did. Does it have y by itself, though? No, and so in that second system, neither x nor y is by itself. Now, we could get it by itself, but in each case, whether we solve for x in the first, or y in the first, or x in the second, or y in the second equation, we'd have to do multiple steps. In other words, we've had a lot of groundwork to do if we wanted to use the substitution method. And so there's another method, the elimination method, that's going to be quicker and easier than substitution if I don't have a coefficient of 1 on any of my variables. So we'll be eliminating one variable in our system in order to find the solution set. Instead of substituting an expression for x or y to result in a single equation, single variable, we'll be adding the two equations together after making opposites in the x's or the y's and eliminating that variable so we have a single equation, single variable. And let's go ahead and see what that's going to look like. And so our steps for the elimination or linear combination method. First, we're going to line up the equations in standard form. Then we're going to go ahead and multiply one or both by some number if necessary to make exact opposites in either the x's or the y's. Third step is my favorite step. We'll go ahead and add those equations together, and one of the variables will be eliminated. And that's why it's called the elimination method. We'll solve for the remaining variable and use either of the original equations to get the other. And then we'll go, of course, going to check our answer as a point x comma y. So let's go ahead and see what it looks like. Just watch for a minute. Right now, is x alone? No. Is y alone? No. But I'm lined up y's over y's, x's over x's, number over number. So what I'm going to do is purposely multiply the second equation by some number. I'm going to make exact opposites in, I'm going to multiply by 2 all the way through to make exact opposites in the x's. So if I rewrite the first one as is, 2y minus 2x equals 2, and I rewrite the second one now after multiplying through both sides, every term by 2, I get 2y plus 2x equals 10. Now take a look, I've created exact opposites, in this case, in the x terms. Negative 2x is the exact opposite of positive 2x. And so what I'm going to do now is add the two equations together, and when I do so, I'm going to create a single equation with a single variable. So I'm going to now add straight down. 2y plus 2y is 4y. Negative 2x plus 2x is 0x's. The x term drops out. It's eliminated. 2 plus 10 is 12. Everybody check it. we've created a single equation with a single variable. Now it's easy to solve for y through division. I'll divide both sides by 4 and get y equals 3. I can now go back into either my original equations and find the missing coordinate. In this case, I know y. I'm going to go find x, and it looks like the second equation would be easier to do so. You can use either one. So I'm going to plug in 3 for y in the second equation. I'll go ahead and rewrite that. Well, I'm going to plug this 3 in for y, and then solve for x by subtraction. I get x equals 5 minus 3 is 2. I'll box my answer as a point, 2 comma 3, and check in the original. Does 2 times 3, 6, minus 2 times 2, 4. Does 6 minus 4 equal question mark 2? Yes. Second equation, does 3 plus 2 equal 5? Yes. Feeling good about that. So we found a solution point, right? We found a solution point. That's pretty awesome. All right, let's go ahead and take a look at a word problem then. 131 tickets were sold at a recent drama production. Student tickets cost $4 and adult tickets cost $7. How many of each type of ticket were sold if the total revenue is $617? This is a classic example of when I would use systems, right, as a problem-solving strategy. I've got some different information here. At the end of the day, I need to determine how many student tickets were sold and how many adult tickets were sold. So what I'm going to do is go ahead and let x equal the number of student tickets sold. Let's define our variables. Let's let y equal the number of adult tickets sold. We can then write a system using the given information. I know that 131 tickets were sold to a recent drama production. I don't know how many student tickets were sold. I don't know how many adult tickets were sold, but I do know that together, student tickets plus adult tickets equals 131. Next, student tickets cost $4 each, and adult tickets cost $7 each, and the total revenue was $617 for the drama production. So we could go ahead and write a second equation that takes into account this dollar contribution. So I don't know how many student tickets X were sold, but I know that each one contributed $4 towards my total revenue. When combined with $7 for every adult ticket Y sold, produces a total revenue of $617. This is why the elimination method is sometimes called the linear combination method. Linear combinations, because here, this reminds me of our standard form linear combinations, like 2 pounds of cashews, right, plus the 3 pounds of peanuts equals my 5-pound mixture that cost $8.49 or whatever. Back from Unit 2. All right, so I've got my system. I'm all lined up in linear combination form. Now I'm going to purposely multiply one or both equations by some number to create exact opposites in either the x's or the y's. Is positive 1x in blue the exact opposite of positive 4x in red? No. Is positive 1y the exact opposite of positive 7y? No. But I can create exact opposites if I purposely multiply this top equation all the way through by -4. I'm going to multiply that top equation all the way through by -4 and rewrite. If I were to do that, I would get -4x minus 4y equals -524. Somebody better check that. Bad things happen when Mr. Fritz starts doing things in his head. I was never good with numbers. Go figure. Negative? Thank you so much. Yikes. Like caramba, see? And I'll rewrite the second one as is. No change there because I wanted to make exact opposites. Then the second one was already 4x plus 7y equals $617. Why have we done this? Take a look. We've created exact opposites in the x term. So now when I add the two equations together, my favorite step, positive 4x combined with the negative 4x is 0x's. And they've been eliminated. Negative 4y plus 7y is 3y equals. And then we'll go ahead and do this difference. This looks like 74 plus 17, 84, 91. No. 81? No. 93? Ah! Very nice. And now we can solve by division. It looks like 1, 2, 30, 31. So $31? That seems kind of pricey. No, what do I stand for? What do I stand for? Cody? Good. So it looks like 31 adult tickets were sold. Where can I go to figure out the number of student tickets? Either equation. If you have your choice, which equation would you rather use? Aaron?
The top one.
The top one, I'm down. The top one looks a lot easier to use than the bottom one. So I'll go ahead and rewrite the top one. X plus y equals 131. We saw that y is 31. So it looks like X must be 100 tickets. So what have we found at the end of the day? It looks like 100 student tickets were sold and 31 adult tickets were sold. And we're going to do a little adventure and try cursive out on the smartboard. 100 student tickets were sold. And 31 adult tickets. I'm trying. Awesome. Great. So the elimination method is my favorite method, right? I like creating exact opposites and then adding. It's also efficient. And so as I look at the work for this example and compare it with even my substitution, I think that the elimination method is more efficient. Go ahead and tell your partner which equation could be multiplied by some number, right? So that exact opposites are created. Go ahead and quietly decide with your partner a plan of attack. How could you create exact opposites in one of the variables? Be ready to share when I call on you. Okay, so how would you create exact opposites in one of the variables? What would you guys do? Will and Aaron?
Multiply the top one by 2.
Raise your hand if you were going to multiply the top one by 2. That's not the only way, but it's a way that lots of you guys did. Awesome. Let's go ahead and do that. So we'll rewrite this top one after multiplying all the way through both sides by 2. So let's go ahead and do that. 10x minus 12y equals 6. I'll rewrite the second equation as is. 2x plus 12y equals 12. And Will and Aaron have made exact opposites in which variable, right? They've made exact opposites in which variable? Mark?
The y.
The y. So we'll go ahead and add these together, and the y's will disappear. They'll be eliminated. After adding the two equations together, I get a single equation, single variable, and I can solve through division. Dividing both sides, I get x equals 18/12, which reduces nicely. Looks like x is going to equal 1, 2, 3 halves. So I'm getting 3 halves for x. Now I can go to either equation. And substitute in for x to solve for y. But as I look at my coefficients, which equation is going to be easier to use this time? I mean, if I want to figure out what y is, do I want to plug in x to the first equation or the second equation? Which would you rather use? Joe? If I want to figure out what y is, knowing that x is 3 halves, a fraction, which equation looks easier to work with? The top equation or the bottom equation?
Bottom.
The bottom, how come?
Because if you plug in 3 halves and it'll just be 3 plus 12y equals 12.
Absolutely. That coefficient of 2 in the second equation is even. It's going to get rid of this denominator of 2 here versus the top one is going to create a fraction. 5 times 3 halves is going to be 15 halves. It's still a fraction. And so when we have the choice, be purposeful in your selection. I'd rather use the second equation just like Joe because then I won't have to work with fractions as much. I mean, don't get me wrong. I love fractions. Fractions taste good. Decimals taste good. First thing in the morning, I have myself a big bowl of fractions. No, but we want to make things right as easy on ourselves as possible. So I'll go ahead and rewrite that second one. 2 times x plus 12y equals 12. We'll go ahead and plug in our 3 halves for x. Work it out. So 2 times 3 halves is 3 plus 12y equals 12. Subtract 3 from both sides. 12y equals 9. Divide both sides by 12 and reduce. I get 9/12. And I'll go ahead and reduce that. That looks like 1, 2, 3, 3/4. Is that right? 3/4. All right, moment of truth. 3 halves, comma, 3/4. We'll see if we can't check this. So 5 times 3 halves is 15 halves. 15 halves minus 6 times 3 is 18/4. That's 9 halves. Does 15 halves minus 9 halves equal 3? Yeah, that would be 6 halves, which is 3. Good. 2 times 3 halves is 3, plus 12 times 3/4 is 9. Does 3 plus 9 equal 12? Yes. Love it. Jeepers, the solving was harder than the checking. I'm saying the checking was harder than the solving. What questions do you guys have about this elimination method? Elimination method? Okay. So let's go ahead and show me that you get it. Multiply one or both of the equations by some number to create exact opposites. And this time be careful with your number selection. Which variable did you make opposites in? Which variable did you make opposites in? Caitlin?
Y.
Y? You made opposites with Y? So to make opposites with Y, right? To make opposites with Y, then which equation did you have to multiply by what? Nathan? Bottom by -2. Raise your hand if you multiply the bottom by -2. Who else used that strategy? That's not the only strategy, but a lot of you use it. That's awesome. Let's go ahead and rewrite that bottom one. I would get positive 6x minus 6y equals positive 42. On top, I'll rewrite as is, no change, 8x plus 6y equals negative 14. Now we've gone ahead and created exact opposites in the y terms as Caitlin specified. So let's add top to bottom. Line them up. 8x plus 6x, 14x plus 6y minus 6y, drop out y's. Yay, they're eliminated. And then negative 14 plus 42 looks like 12, 30, 28. Right, 28. So it looks like y equals, nope, x equals 2. I can go back into either one. I'll go to the top because it was positive. So 8 times x plus 6y equals negative 14. Except I'll put in 2 for x. And I'll get 16 plus 6y equals negative 14. Then I'll go ahead and subtract 16 from both sides and get 6y equals negative 30. Is that right? Negative 30? Negative 30? So then I'll get, divide both sides by 6. Go Gadron. I'm getting y equals negative 5. I'm not so sure about this. So I'm going to go ahead and write my answer as a point, and then I'm going to check it. All right? I'm not feeling too positive about this. 2, negative 5. Let's see. So 8 times 2 is 16. 16 plus a negative 30. Does that equal negative 14? Yeah. Negative 3 times 2 is negative 6. Plus 3 times negative 5 is negative 15. Does negative 6 plus a negative 15 equal negative 21? Yes, it does. No reason to worry. That's correct. So raise your hand if you also got 2, negative 5. Well, it's got 2, negative 5. Great work, you guys. And if you didn't, that's okay. Just want to make sure that you correct it. Make a correction here so that you can produce 2, negative 5. I would not want to solve that system by substitution. If you had solved that by substitution, you would have to solve one of the equations for one of the variables, and they all have coefficients other than 1. That would have been a real pain. And you would have created fractions. And so I like this method much better. All right, so let's go ahead and take a look at our last linear combination example. As I scan this problem, substitution method does not look fun. It looks to me like I don't have a coefficient of 1 on any variable, so I'd have multiple steps to solve. And at the same time, elimination method, right? Elimination method, I can't create exact opposites by multiplying by an integer in one step. What I'm going to do is multiply both equations by different numbers to create exact opposites. And so here I'm going to go ahead and purposely choose to make exact opposites in either the x's or the y's, and I'm going to do a double multiplication. One to each, one multiplier through each equation to create exact opposites. Would you rather make exact opposites in the x's or the y's? You want to make exact opposites in the x's or the y's? Rachel?
We can't do either by 2.
No. That's okay. We're going to multiply each equation by a different number to create exact opposites. I just want to know if you want to get rid of x's or if you want to get rid of y's. We can do either one, and it doesn't matter.
Why?
You want to get rid of y's? All right. So if we want to get rid of y's, we need to make exact opposites on the y term. Is positive 5y the exact opposite of positive 2y? Carson?
No.
No, it's not. We're going to create opposites by purposely multiplying both equations by some number. So let's think about the first number that we can make exact opposites by. 5y and 2y. I could multiply and create exact opposites. What if I multiplied the top all the way through both sides by negative 2? If I did that and rewrote the top, I'd get positive 20x minus 10y equals positive 10. Meanwhile, the bottom equation, I need to make exact opposites in the y's. Rachel wanted to get rid of y's, so I'll multiply bottom equation all the way through, and I need to make exact opposite of negative 10y. What's the exact opposite of negative 10y? Ian? Positive 10y, so what would I need to multiply the bottom equation through by? Caroline?
What was the question?
Oh, to make exact opposites in the y's, Ian says we need positive 10y to be the exact opposite of negative 10y. So what number do I need?
5.
Good, all the way through. Thank you. Do it. 5 times 3x, 15x. Plus 5 times 2y is plus, there's my exact opposites, plus 10y equals 5 times negative 9 is negative 45. Now we're ready to use, right, the addition step. My favorite step, we're going to add straight down and get rid of those y's. So 20x plus 15x is 35x. The y's disappear, equals, and now I'm adding 10 plus a negative 45 is negative 35. Could it be, after all those coefficients floating around and big numbers, that I get x equals negative 1? That's pretty sweet. And now you can go into either of the originals. I think I'll go into that second one and rewrite it. 3 times x plus 2y equals negative 9. But I'm going to put in negative 1. So negative 3 plus 2y equals negative 9. Going to add over. Negative 9 plus 3 is negative 6. And then divide both sides by 2. I get negative 6 divided by positive 2 overall is negative 3. I'll go ahead and check my answer, negative 1, negative 3. Let's check it. So negative 1 in for x. Negative 10 times negative 1 is 10. 10 plus a negative 15, that's negative 5. 3 times negative 1 is negative 3, plus 2 times negative 3 is negative 6. Negative 3 plus negative 6 is negative 9. Something. It does check out. And so we've got our solution to the system. And again, substitution would have been a real pain to do with that method. Great. All right. 2 things to go. So you guys already showed me. We're going to skip that. We're going to skip that. And we're going to jump to our final 2 examples. If you guys take a look at 2x minus 3y equals 13 and 4x minus 6y equals 20, we could create exact opposites. We could create exact opposites in either the x's or the y's. I think I'm going to make exact opposites in I'll do the x's. So I'm going to multiply the top one through by negative 2. All the way through, if I did negative 2 all the way through, I'd get negative 4x plus 6y equals negative 26. My second equation I'll rewrite as is because I wanted exact opposites in the x's. So 4x minus 6y equals 20. Now when I go for my favorite step, adding the 2 equations together, negative 4x plus 4x is 0. Plus 6y minus 6y is also 0. So on the left-hand side of this equation, I get 0. However, on the right-hand side of the equation, I get negative 6. Does this equation make sense? Does 0 equal negative 6? No. What's going on here?
There's no substitution.
No, I've created an algebraic sentence. I followed the rules, right? But I've created an equation that is never true. And that's my algebraic indication that there's no solutions to this system. In fact, it's inconsistent. Graphically, we can consider what this looks like. If I consider this first equation, 2x minus 3y equals 13, and rearrange it in slope-intercept form to graph, I get y equals positive 2/3 x minus 13/3. If I rearrange the second equation to graph in slope-intercept form, I get y equals positive 2/3 x minus 26. I'm going to go to 10/3. As you look at these 2 lines, Rachel,
Is there ever any unreal solutions?
we're not going to allow non-real solutions to systems in this unit, okay? We certainly will deal with non-real solutions in quadratic equations and polynomial equations. But when we're working with our systems this unit, we're not going to have non-real solutions. We could if we were dealing with quadratics within my system. However, each of these are linear equations, and so you don't have to worry about it. Good question. Guys, consider the graphs of those lines. If I made a quick sketch in my head of that first equation in blue, y equals 2/3 x minus 13/3, that would look something like this. If I made a quick sketch of the second equation, in green, it would look something like that. How many times do those lines intersect? None. Parallel lines don't intersect at all, right? So how many solutions are there? No solutions. Graphically, parallel lines have no solution, no points of intersection, so the system has no solution. Algebraically, I've created an equation that is never true. That's my algebraic indication that there's no solution. Either way, we're not done unless we say no solution. So this is what we'd have to box. Just like we boxed 2, -3, we'd have to box no solution. Awesome, guys. That's pretty sweet. So graphically, they're parallel lines. I'm sorry, I'm not going to feel right if we don't. There we go. Sorry, I know. It's one of those things. I mean, I export this as a PDF and try to post it to the Moodle page, knowing that I didn't put arrows on my lines. I'd be like, wake up in the middle of the night and you're like, I should put arrows on there and I can't go back and I wish I could, but I can't. In any case, let's see what happens when we try to solve this one. I want to make exact opposites in either the x's or the y's, and so substitution method, no coefficients of 1. I'm going to multiply that top one by -3, -3 all the way through on top. That gives me positive 9x minus 12y equals, I don't want -3. I want positive 3, don't we? I want to make exact opposites. So that would be negative 9x plus 12y equals 15. The second equation as is, leave it alone. 9x minus 12y equals negative 15. What happens when we add these two equations together? Negative 9x plus 9x, 0 x's, plus 12y minus 12y, 0 y's, equals 15 minus 15. It's also 0. Oh gosh. Another interrobang in the same class period, 2 in a row. OMG, KIT, BFF. Is this a true statement? Does 0 equal 0? Is this equation sometimes true, always true, or never true? That's always true, right? So what could be going on here? How many solutions are we talking about now? Joe? An infinite number of solutions. Let's consider these graphically. So again, if I were to solve these equations for y, I could make a sketch. I get y equals, looks like positive 3/4 x plus 5/4, and I get y equals negative, positive 3/4 x plus 15/12 reduces to 5/4. Take a look at that. If I graph the blue line and then went and graphed the green line. Oh gosh, I'm gonna do this again. Yeah, just because I want it right on top of it. So if I did that, and I plotted the two lines, I get what we call overlapping lines, right? Overlapping lines. How many points do they share? An infinite number of points, and so we have an infinite number of solutions. There's one, there's one, there's one, there's one, there's one, there's one. My hand's getting tired. do we say? Well, we don't say 2 comma negative 3. We don't say no solutions. We say infinitely many solutions. There's an infinite number of ordered pairs, x comma y, that satisfies both of those equations in the system. So infinitely many solutions is what we say. Infinitely many solutions. So any point on either of those lines would be a solution to the system. Great. That's for you to print. So let's go ahead and summarize our findings for the day. Don't call out. I want you to go ahead and write down a response with your partner and be ready to share with the class. When is substitution method the best method to solve a system? And what must be true before you substitute? Then with your partner, discuss and write, when is linear combination method, or elimination method as it's also known, the best way to solve a system? Answer what happens when we get an equation like 2 equals negative 6 versus 0 equals 0. And then how can you be sure you found the correct solution to a system? Please be ready to share. Okay, go ahead and share your response with the class when I call on you. When is substitution method the best method to solve a system? Samantha?
When x or y are alone in one of the equations.
Absolutely. When x and y are alone or easy to get alone in one of the equations, substitution method is the easiest method to use. So when the x or the y is easy to get alone in either equation, then, right, then it's going to be easy to use substitution method. What must be true before you can substitute? So before you can substitute, what do you have to be sure of? Hannah?
The left side equals the right side.
Oh, and what has to be on the left-hand side or the right-hand side? A single variable. So we need a single variable alone, right? We need a single variable alone. Perfect. We need x equals blah, blah, blah with y, left side equal to right side, or y equals blah, blah, blah with x's in it. Good. When is linear combinations the best method to use? So when do we want to use linear combinations then instead? Megan?
When there isn't a single variable isolated.
Good. And so if it's difficult to get x or y alone, then we could consider using linear combinations. Or if they're already lined up, right? If they're already lined up. No coefficients of 1. No coefficients of 1. Maybe it's difficult to solve for a variable or isolate one of the variables. Or maybe they're all lined up. With exact opposites in the x's or the y's. Even if there's a coefficient of 1, I just add them straight away. When solving a system, what does it mean if you generate an equation like 2 equals negative 6? Right? What's that telling you when you generate an equation like 2 equals negative 6? Jarrett? No solution. So this equation is sometimes true, always true, or never true. 2 never equals negative 6. And so that's your algebraic indication that there are no solutions. Good job. Raise your hand if you had no solutions for that first one in number 4. No solutions? Good. Thank you. Hands down, no solutions. Versus an equation like 0 equals 0. Right? That's an algebraic indication that what's true about that system. What's true about that system? Jacques? Yeah, there's an infinite number of solutions. If the equations then have a single, any ordered pair that satisfies the first equation is guaranteed to satisfy the second equation. So infinitely many solutions. And lastly, how can you be sure you found the correct solution to a system? So how can you be sure that you found the solution to a system, right? Casey?
By checking, by putting x and y into the equation.
Absolutely. So we can plug into the original equations and see if it makes true statements. So I'm going to say plug into originals to check. At the beginning of class in Bellwork, we had a couple other ways to check. And so what else do we do to check? Cody?
If they're equal in the table.
Yep. So we check with the table. And lastly, what can we do with our grapher? Jacob?
You could check put the equations into the y equals 0.
Absolutely. We could always do second calc 5 is intersect feature. Awesome work, you guys. That was great stuff. There's a printable for you. And here, don't neglect to include your reading questions 4.1 and 4.2 for assignment number 2. You've got a nice chunk of time to work. I'm going to go ahead and stop the recording and upload it to our Moodle site so that we'll be good to go.